Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so in today's lesson, we are on the topic vectors in 2D. And then we have this question 2 here. It says, learners doing a force board practical finds that the following forces could balance object A, right? So if they ever talk about forces balancing out an object, that means we know that the whole system here is at equilibrium, right? Now, if the system is at equilibrium, these are the few things that we know. We know that F net is equals to 0 newtons. That's number one. And then we know that from there, we can be able to have a closed vector diagram. And then also, again, we know that the forces balance out. The forces balance out. So what do I mean by that? The horizontal forces. In terms of the horizontal forces, that means the left forces are equal to the right forces. And then in terms of the vertical forces, we know that the upward forces would be equals to the downward forces. So these are some of the things that we know when they say the system is at equilibrium. So it's not moving at all. It is stationary there, right? So meaning that our F net is 0 newtons, and then closed vector diagram, then the forces balance out. Now we are being asked in 2.1, what is the magnitude of the resultant force of the system? We already know. You can even see it's 1 mark. So you're just supposed to say it's 0 newtons, right? So this is not on, it's 0 newtons, guys. Then 2.2 says state Newton's first law in weight. So to quickly state that, Newton's first law in weight simply states that a body will remain in its state of rest or uniform motion, or we can say will continue moving at a constant velocity, then unless an unbalanced force acts on it. So for 2 marks, that's how you are expected to define Newton's first law in weight, right? Then let's proceed. We are given a 2.3. It says 2.3, calculate the components of the force in string T1, right? Now, looking at T1, we can see that this force here is acted at an angle of 60 degrees to the vertical line, to the y-axis. But then I need you to note something, NB. Whenever we are trying to resolve a force into components, the angle that we should consider should always be between the x-axis and the force, right? So looking at this, we can see that this 60 degrees here is between the vertical, right, line, which is the y-axis, and then the force. This is not the correct angle to use. Whenever you are given a situation like this, always note it in your mind, at the back of your mind, that you need to find the angle in here. Now, how do you do that? You know that if you have to close off here, this will form an angle of 90 degrees. So in order to find the angle in here, you just need to say 90 minus the given angle. So that's 90 minus 60. We find an angle of 30 degrees. So that means the suitable angle to use for tension number 1 when we are resolving it into components is 30 degrees, not 60 degrees. Again, they did the same thing with tension 2. They gave us 30 degrees, but it's between the y-axis and the force. Note the angle should be between the x-axis and the force. So how do we find the suitable angle to use? You just go ahead and say 90 minus 30, and then you will have 60 degrees here. So the suitable angle to use for T2 is 60 degrees, and for T1 is 30 degrees. I hope that makes sense. Now, let's calculate the components. Now, we know that the components that we have are the horizontal component, which is represented by Fx. But then now that we have our force as tension, we can just go ahead and indicate it as Tx, right? And then we also have the vertical component, which is represented by Fy. But since we have the force as tension, we can just go ahead and represent it as Ty, right? Now, because this is Tx of tension number 1, let's call it Tx of 1. And then we just gonna go ahead and say T cos theta. So I'm pretty sure that you are aware of this formula. Then tension here, we substitute T1. Then this is 381.05, and then cos 30 degrees, note. And then this will give us a value of 330 newtons. But then remember, resolving this, if we are to resolve here, this should look like this. So let's resolve the components. So when we are resolving Ty, we should have the vertical component, which is Ty, and we should have on the left-hand side the horizontal component, which is Tx. Why? Because Ty is pulled to that side. So that means our Tx will be pulled over to the left-hand side. And then since it's being pulled up there, so that means our Ty would be also pulled up there, right? So that means 330, remember this is horizontal component. So this should be 330 Newton west. You can either say west or left, right? Then the Tx, now to calculate Ty, meant to say Ty of 1, just going to go ahead and say T1 and then sine theta. Now we are calculating the vertical component. So what is my T1? Again, I substitute 381.05. And then sine 30 degrees. When I punch this into my calculator, it gives me 190.53 newtons. But then look at this force here, it's going up there. So it's in the northern direction, or you can just say the direction is up, right? So either way, you'd be correct. Then that's how you calculate the components of the force in string T1. Now let's get to 2.3.2. Now here we are required to calculate the components of the force in string T2. So once again, this is T2 of X. Then we have T2 cos theta. What is the magnitude for T2? That's 660. Then we have cos. The angle that we are supposed to use, remember it's not 30, is 60 degrees. Then if we punch that in our calculator, we have 330 newtons. But then remember, if we are to resolve this, we have our Tx over this side, and then we have our Ty up there, right? Then this should be 330 Newton east. And then to calculate the vertical component, that's T2 sine theta. So we have 660 sine 60 degrees. Then punching that in your calculator, you have 571.58. Then it's going up there. The direction is north, or you can say it's going up, right? Then just like that, you have calculated the components of the force both in T1 and T2, right? So nice. Now let's go to 2.3.3. It says the mass of object A. So now we are to calculate the mass of object A. Now, how are we supposed to do that? Note, we go back to the fact that we said this system is at equilibrium. Now, remember, we said when the system is at equilibrium, the forces balance each other out. Left forces are equal to right forces, and then upward forces are equal to downward forces. Now, let's draw a vector diagram for all of this with resolved vectors. So remember we had T1x here, and then over to this side we had T2x. Then down here, let's just label this the force of A. And then up there, we have Ty of 1, but then also up there because even Ty of 2 was going up north, so we have Ty2. So let's be precise with the sizes that we had. So remember Ty1 was had a smaller magnitude. So let's just say Ty1, and then this one here will be Ty2, right? But then remember we said that since the forces are at equilibrium, left forces are equal to right forces. And we can even prove that by calculations, because for T1x we found 330 Newton, and also here this is 330 Newton. So if we were to calculate the resultant for the horizontal forces, we would find that our resultant is 0 Newton, because this will be 330 Newton minus 330 Newton since they are acting in opposite directions. So our Tx net would be 0 newtons, but then also our Ty net would be 0 newtons. So the reason for this is because of equilibrium. So we are saying that, again, the upward forces will balance out the downward forces. So in other words, what am I saying? This upward forces here must be equal to that. We are looking for the force of A before we can find the mass, right? So that means the force of A will be a sum of these two vertical components. So that's Fa is equals to Ty plus Ty2, right? What did we get for Ty1? That's 190.53. And then what did we get for Ty2? That's 571.58. Now at this point, you need the aid of your calculator. 190.53 plus 571.58. That gives us 762.11.11, right? And then now to calculate the mass, we do understand that since this is at equilibrium, object A is experiencing a gravitational force Fg, and it is also experiencing the tension force, which we said we label it force A, right? Then, if this is at equilibrium, we are saying that the gravitational force for block A is the same as force A there, right? So that means we can say Fg is equals to 762.11 Newton, because the forces balance each other out, and this is at equilibrium. Then to calculate the mass, that's mg is equals to 762.11. This is our mass. Our g is a constant, that's gravitational acceleration, 9.8, is equals to 762.11. Now to calculate the mass, we just need to divide both sides by 9.8. Then what is our mass? If we divide that out, we find a value of 77.77 kg. That's how you would solve that one. So easy peasy, lemon squeezy. Okay, so we have yet another question too. It says the diagram below shows three forces P, Q, and R of 5 Newton, 3 Newton, and 4 Newton respectively, acting on an object in the same Cartesian plane, right? And then here in 2.1, they say give a reason why the three forces are classified as vectors. So we know what a vector is. A vector has both magnitude. So this is a physical quantity that has both magnitude and direction. So if we are to look at why these three forces are classified as vectors, we can say that they have magnitude and direction. The direction is represented by the arrows, and then we can see the magnitude here is represented by those sizes there. So we can say that all these three forces have both magnitude and direction. Nice. Then 2.2 says determine the magnitude and direction of the resultant force, either by calculation or by accurate construction and measurement. Then for this question here, we'll just be using mainly the calculation. So I won't be going into the accurate construction and measurement. I'll just only be focusing on calculation. Then to do the calculation there, what we need to do first is check R. Here we can see that R is the only force that is exerted at an angle. That means it needs to be resolved to the vertical component and horizontal component. So in order to do that, let's first start drawing out P here. Then it's going up, and then we can see Q here. It's going to the right. Then let's include our magnitudes. But then this one needs to be resolved. To resolve this one, we can see that it is in the fourth quadrant. So that means its vertical component must be here. So this would be FYR going down there. And then its horizontal component must go all the way to the right. Right. So we can see that. So this is FXR. That's how you resolve the components. And then now let's include them to our vector diagram. So this would be Fx of R. And then right here, we will have Fy of R. But then remember, once we resolve this, we cannot go here and say 4 Newton, 4 Newton. That means now we have to calculate the magnitude of this components, right? Now to calculate the magnitude of the components, let's start with Fx of R. This will be F cos theta. So my force is 4, then cos 45 degrees. We can see that the angle that we are given here is between the x-axis and the given force, so it is in the correct place. Then we have 4 cos 45 degrees, and then this will give us a value of 2.828. So let's just round off to at least 3 decimal places because it is not the final answer. Then let's calculate the vertical component FYR. This would be F sine theta. So this is 4 sine 45 degrees. When you punch that in your calculator, it should give you exactly the same answer because remember, sine 45 and cos 45, they are equal according to your trigonometry. Then this is 2.82 newtons. And then where is it going? It's going down, but this one is going to the right. Now that we have that, we can include the values here. We have 2.828. Also, this one is 2.828. So newtons. Now, at this point, we want to calculate because we can see that 2 forces going to the right, and then we have these 2 forces going in opposite directions, but then they're on the vertical plane. So we only need the Fx net for the horizontal, and then we need the Fy net for the vertical. So that's the next step. Let's calculate the Fx net. So we can calculate the Fx net by taking all the horizontal forces. So they're both in the same direction. So they have to add up. This is 3 plus 2.828, right? And then adding the 2, we have a value of 5.828 newtons, and then to the right. But then if we are to calculate the Fy net, which is the resultant for the vertical, we can see that they're in opposite directions. So we need to subtract 5 minus 2.828. Then if we are subtracting that, we have a value of 2.172 newtons. And where is it going? It's going up, right? Because we can see that the bigger vector here is P. So it needs to take the direction of the bigger vector. Now, since we have this, we can now try to draw a closed vector diagram, a right angle triangle. representing this, right? So now we have a magnitude representing the horizontal forces, and we have a magnitude representing the vertical forces. So this is what we are going to do. It's to the right, so we need to indicate this is 528 newtons. And then this here is up, so we need to indicate it like that. So it's up. It needs to be right in this direction. Remember, it's tail to head. Then this will give us 2.172 newtons. And then to represent our closed vector diagram, we need to take it from here and then close it off like that. So still I'm doing a tail to head method, right? So this is my tail to head method. Now, the hypotenuse side that I just drew here will represent my resultant force. So this will represent my resultant force. That means in order to calculate the resultant force here, now I'm working with 2D, right? So I need to say my Fres is equals to Fx net square plus Fy net square. So I'm using Pythagoras theorem. So this is Fres square is equals to Fx net square plus Fy net square. My Fx net was 5.828, and then square that. My Fy net is 2.172, and then square, right? Then that means at this point I can just say my Fres and then put all this inside a square root. Then when I punch all that, my Fres is supposed to be 6.22 newtons. Right, but then I'm not done. Remember, I must show the magnitude and direction. I only have the magnitude of the resultant force. How do I show the direction? Remember, I'm now on a 2D, and then it is impossible to say left, right, up, down when you have a diagonal line like this. So at this point, you need to find your direction in terms of an angle. So how do you do that? You use the trig ratio tan. So this will be to find the direction. We have tan theta, and then we know according to SOHCAHTOA, tan is opposite over adjacent. So if we have to have our angle here, our opposite will be 2.172, and our adjacent side would be 5.828. Now to calculate the angle, need to leave the angle, then say tan 2.172, 5.828. Then punching all that in your calculator, you have your theta as 20.44 degrees, right? So in conclusion, we can say that our resultant force is equals to 6.22 Newton in the direction of 20.44 degrees. Right. And that's how you're supposed to work out that question. Right. So make sure that you pause throughout the video and slowly try to understand how you go about solving this question here. And then let's proceed. Now we are given a box of weight W, 60 Newton, hangs on a ceiling as shown in the sketch below. A horizontal force F acts horizontally to the right through knot S. The knot S is in equilibrium. Now they say, explain what is meant by knot S is in equilibrium, right? So to explain that, what is the meaning of knot S being in equilibrium? It simply means that here, remember when we say equilibrium is always related to F net being equals to 0 newtons. So that means all the forces acting at point S have a resultant force of 0. Right. So this is the meaning of that. So knot S is in equilibrium. That means all the forces that are acting around knot S here, they have a resultant force of 0 newtons. Then 2.4 says, draw the triangle of the three forces T, F, and W. Clearly label the forces and all the angles, right? Now, another thing that we know about equilibrium is that when we have this, we are able to draw a closed vector diagram, right? Our closed vector diagram should always be a right-angled triangle. So this is the triangle that they are asking us to draw. And then it's very simple to draw that triangle because it's just, I call it the cut and paste method, because all you do is just take the W as it is. We know that this force is acting downward like that, and then just indicate its direction. So we are still using the tail to head method. So this will be our W, which is 60 Newton. And then we can go ahead and take our force F here, just like that, indicate its direction. So this would be force F. And then we can go ahead and take force T here. And then just like that, remember head to tail. So you need to have a straight line like that. So let me just do it like this. Yeah. So this will be representing our tension. And then here we have our W. Now to indicate the angle, remember here we had 55. So exactly in that position, we have 55 degrees. But then remember this here forms the right angle, triangle, the right angle. And then, so knowing that the interior angles of a triangle should always give us 180. If we say 180 minus 90 minus 55, we have 35 degrees, right? And just like that, you have a closed vector diagram. Or if you don't want to follow that order, you can still start with your force here in that direction, then go ahead and indicate your W, and then close it off with your tension. So only thing is that it will be facing down like that, but then it is still the same thing. So here, you would still have your force 55 degrees, and then here you'd still have 90, and then up here you'd have 35 degrees. So looking at these two triangles, they're all the same thing, right? Then to calculate the magnitude of force F and tension T, this is what you're supposed to do. Remember, you now have a right angle triangle. That means the trig ratio can now apply, right? So you have SOHCAHTOA, and then to calculate force F and calculate force T, this is how you can go about it, right? Now you have the angle in here, and then you are looking for force F. Remember, this is your adjacent side, this is your hypotenuse side, and this is your opposite side to the angle 35 degrees. To look for F, you can just go ahead and say, if I'm looking for the adjacent and I have the opposite, what trig ratio can apply here? We have tan for that, opposite, adjacent. So I would go tan 35 degrees, and then what is my opposite? That's 60, and then what is my adjacent? That's the F I'm looking for. So this will go F is equals to 60 over tan 35 degrees. And then calculating your value for F, you will find that is 85.69 newtons, right? Then to calculate T, you have the opposite side, but then you are looking for the hypotenuse side. Opposite and hypotenuse, that's sine. And then you have sine 35 is equals to your opposite, again, is 60. And then what is your hypotenuse? That's the T you are looking for. And to calculate for T, you just go 60 over sine 35 degrees. Then tension is equals to 104.61 newtons. And just like that, you have calculated both the magnitudes of F and T. So that's how you were supposed to solve that one. So make sure that you go about it slowly and try to understand whatever that I did. So this is where we're just going to end our lesson for today. And then please press the thumbs up button if you have enjoyed the lesson and you have found it helpful. And then also don't forget to share the link with your friends and classmates. And if you've been watching these videos and haven't subscribed, please press that subscribe button right now. And don't forget to also press that bell notification button so that you are notified of every video that I post, right? So that you're always up to date. And then with all that being said, guys, ciao.